Okay, so let's begin. Welcome everyone for the last session of the conference. And let me begin by saying that it's a great pleasure and honor for me to be here. And obviously it would be very improper for me to thank the organizers for this. But I would like to thank Jean for taking me as a student and for his many insights and for his generosity with his time and for everything I learned from here. And obviously I wouldn't be here otherwise. And I also want to thank him for his 500 papers or so that we are celebrating in this conference, without which this conference wouldn't exist. Um, so the topic of the first talk of the session will be on ergodic theory, and Jean contributed a lot of results to ergodic theory. In particular, in the late 80s and early 90s, he worked on ergodic averages, convergence of ergodic averages along polynomial sequences, and he has some very deep results there. And now I just want to highlight more recent work of his, which is about effective results in ergodic theory, which is more related to the talk that is coming. So this is a joint work of his with his collaborators Elon and Philippe Michel and Akshay Venkatesh. And in that paper, they give an effective version of Rudolph's theorem. So Rudolph's theorem is about measures which are on the unit on the circle R mod Z, which are invariant under both the ×2 and the ×3 map. And Rudolph proved that if such a measure has positive entropy, say entropy equals alpha, then this measure has a Lebesgue component of mass alpha. And in this paper, Jean and his collaborators give an effective version of this result. So roughly speaking, it says that if you have a measure which has a certain amount of entropy at a given scale, and you take a test function, then the integral with respect to some push forward of this measure along the ×2 ×3 orbit will be at least alpha times the integral with respect to the Lebesgue measure. This is a very nice paper which combines many ideas with some very deep number theoretic input and also some nice combinatorial ideas. The second talk that we will have after the break will be about Bernoulli convolutions. And I will not tell you what Bernoulli convolutions are, because probably Emmanuel will. But they are analogues of another construction called Fürstenberg measures that Jean studied a lot recently. So if you take a probability measure on SL2R and you start convolving this with itself, then eventually it will converge to a measure on the boundary, and this is called the Fürstenberg measure. And it is a very subtle and delicate issue to say something about the regularity properties of this measure. And it was Jean who gave the first examples of a finitely supported measure on SL2R whose corresponding Fürstenberg measure is absolutely continuous. And by this, he actually disproved the conjecture. And in another paper, he studied a particular example which was motivated by the Anderson-Bernoulli model on Z, which is something that we heard more about yesterday. And what he managed to prove there is that if you take the disorder to 0, then the dimension of the Fürstenberg measure will converge to 1. And he used this to say something about the integrated density of states in the Anderson model. So finally, let me mention two papers of him, which are about the discretized sum product theorem, which is something that Alex already mentioned before. So this result is at the heart of his proofs about the Fürstenberg measures, and so this is a very powerful technique that he developed, and then he mastered it and used it to solve many problems. And yesterday, Jean's advisor told us what he thinks Jean's best time investment was when he solved a major open problem in 10 minutes while being a student. And in the last 8 years or so, I spent many hours on trying to understand Bourgain's papers on the discretized sum product theorem, and I believe that this is my best time investment. And luckily for me, there is a lot of more very promising investment opportunities in his other 498 or so papers. So with this I finish, and it is a pleasure for me to introduce our first speaker today, who is Elon Lindenstrauss from Jerusalem, and he will tell us about effective density of unipotent orbits.
Thank you. So I'm very much honored to have this opportunity to take part in the celebration of Jean and his remarkable body of mathematics he created. It's like, I guess everyone who knows him, my admiration of Jean is really, I don't find the right superlative to use, but you could use your imagination. I know Jean since, to some extent, I guess that's not a very deep sense of knowledge, but as a teenager he would come to our house from time to time when he visited my father, Yoram, in Jerusalem. After graduation, I came to the institute in 99, and Jean was my assigned mentor. I think formally this does not mean so much. I got a letter on the first day here. Well, the first day I got a letter about the new cook. Second day, I got a letter about Jean being my mentor, and that we were supposed to meet at least once a year or something like that. But during that time, I had a joint paper with Jean on entropy of quantum limits, which was somehow, this entropy estimate was a crucial ingredient in work I later did on arithmetic quantum nuclear ergodicity, and his drive, his energy was really the push I needed to start on this project. As a postdoc, what he was really interested in was not this, but Jean was interested in these Anderson localization discrete Schrodinger equations that Wilhelm talked about yesterday, and indeed he was collaborating with Wilhelm and Goldstein very extensively at the time. When I returned as a faculty to Princeton in 2004, fortunately for me, what Jean was most interested in was some product estimates and all the wonderful things that could be done with these things. And this was very good for me because it's much closer to the kind of things that I care about. So I talked to him quite a bit, and the nighttime discussions I had with him were really the highlight, maybe the highlight of my time in Princeton. Jean is fiercely competitive and generous and kind, and these somehow slightly would seem to be competing notions, but not in Jean. So what I'm going to talk about today is somehow related to things I've learned from Jean The analytic combinatorial techniques of Jean are extremely powerful, and usually when Jean proves something, he doesn't just prove it, he also gives results are also quantitative, gives rates, at least in the context of equidistribution. Ergodic theory is a very powerful theory, very powerful method, but it has this weakness that it doesn't give bounds. So I'm going to sort of explain a bit about one attempt to try to begin rectifying this, and this is based on joint work with Gregory Margulis, Amir Mohammadi, who's here somewhere in the back hiding, and Nimi Shah. So I have a group, linear algebraic group, a group of matrices, maybe SL and R, and the subgroup of this group of matrices is unipotent if connected subgroup is unipotent if every matrix in this group has only one as its eigenvalues over the complex numbers. A special kind of unipotent group, and that's sort of very important to understand, this is a key notion to understand this talk, is a spheric subgroup. These are, you pick an element of your group and you look at all of the elements which are contracted by conjugation by this element. Now, since conjugation doesn't change eigenvalues, and since if you're very close to the identity matrix, your eigenvalues will be close to 1, it is clear that a horospheric subgroup is a special case of unipotent group, but not vice versa. So this is an example of a horospheric group. This one parameter 2 by 2 one parameter group in the 2 by 2 matrices. In SL3R, you have two types of horospheric subgroups. You have this three-dimensional group and you have this two-dimensional group. But in SL3R, there are also many unipotent groups which are not horospheric, like this degenerate one-parameter unipotent, this generic one-parameter unipotent, and this two-parameter unipotent group. Notice that somehow these two groups would seem to be of the same size in some generalized sense, but because this group is horospheric, it's much easier to understand its dynamics than this group. Now, the orbits of this one-parameter unipotent group in SL2R modulo gamma are a very classical object. They project, when you project the natural projection from SL2R mod gamma to the hyperbolic plane modulo gamma to a Riemann surface, they project to horocycles. This is this disk model of the hyperbolic plane. These are the geodesics. The horocycles are somehow would look like circles tangent to the circle at infinity. And already Hedlund in the 30s studied these horocycles, and he showed that any horocycle in a Riemann surface of finite area is either dense or periodic. That's very different from, for instance, the behavior of a different one-parameter group, this one-parameter group, the diagonal group, where orbits can basically be whatever they want. They can have any Hausdorff orbit closures of an orbit can have any Hausdorff dimension you want. Of course, okay, it's an orbit, so it will be at least one dimension, but any number between 1 and 3 is a possibility. Most orbits are dense because of ergodicity, but in this game, we don't really care what happens for almost every. It's kind of a mathematical Murphy's law. We don't really care about what happens almost everywhere. We care about the exceptions. Excuse me. Motivated by works of Dani, Furstenberg, and Margulis, Raghunathan conjectured that this rigidity properties of the horocycle flow are part of a much larger picture, that they actually extend to any unipotent flow. And this conjecture was established by Ratner. This is really extremely important theorem. And there were important special cases which had some rather profound implications, proved earlier by Margulis and Dani Margulis. It will be convenient to have one piece of terminology to state the theorem. So if I have some space and a group acting on some space, a group for me is always locally compact or something. The point in my space is periodic for L if its stabilizer has finite covolume in L. Okay, so we all know what it would mean for a flow with one parameter flow to be periodic. Basically means that the point would come back to itself. When you have many parameters, there could be competing notions. That's the notion I'm going to use, that the volume of my orbit is finite. And the theorem by Ratner, proved in 1991, basically says that if I have a group generated by one parameter unipotent groups, I've written it here in the context of Lie groups, but the heart of the matter is actually what happens for linear algebraic groups. And okay, if you work in Lie groups, you need to talk about ad unipotent and not unipotent, because that's what makes sense in this context, but for us, it's not going to be important. But anyway, if you have a group generated with unipotent elements, its orbit closure is nice. So maybe the group is dense and the orbit closure is everything. Maybe the orbit is periodic and the orbit closure is what you started with. Or maybe there's a bigger periodic orbit that of the bigger group that you're dense inside it. That's basically all possibilities. And okay, there were, like I said, some prior results. Some of the motivated Raghunathan in this conjecture. This is, for instance, this result by Dani, that this is true for any horospheric group. And an important case, which was established by Dani Margulis and Margulis, is the case of the group of symmetry group of a quadratic form of signature to 1 acting on SL3R modulo gamma, or maybe especially SL3R modulo SL3Z. So there was, Margulis showed for SL3R modulo SL3Z that any orbit is either periodic or unbounded, and this implied the Oppenheim conjecture, which, at least for homogeneous flows, is a very important moment, because this was the first time where sort of a major open problem in number theory was proved by dynamical techniques. And then later Dani Margulis transferred to get the full orbit closure classification in this case. Dani Margulis went further to talk about a one-parameter subgroup of this three-dimensional group. Somehow, the smaller the group is, the harder it is to classify orbit closures as a general rule. And there were also results by Nimi Shah, which basically were overshadowed by the work of Ratner, which was announced and published at the same time for SON1. It's important to realize maybe that what Ratner proved was stronger than just density. She actually proved that every orbit, if you have a one-parameter flow, every orbit is not just the closure is nice, but the orbit is equidistributed in the closure. In particular, unipotent flows have this nice property, which not so many flows have, that every point remembers, like some kind of migratory animal, remembers where it started with and comes back to it infinitely often. The key part in Ratner's approach was classifying invariant probability measures, and these important theorems that I've mentioned were extended to the S-arithmetic context by Ratner and by Margulis-Tomanov, and these have numerous applications, from non-vanishing of L functions to the local global principle for representing a quadratic form with a higher degree inside a higher degree form. So there are numerous applications here which are quite unexpected. So, okay, that's sort of background. Now I want to talk about the quantitative theory. So, what is known quantitatively? So one case which is known quantitatively in, I think, complete generality is the case of horospheric groups. And this started quite early with work of Sarnak from 81, and reported work of Bourgain, and then further works by Flaminio Fornis, Strombergson, Sarnak-Ubis. This is understood because of the relation between the properties of individual orbits for horospherical groups and properties of generic, the mixing properties of the corresponding flow, the corresponding element which defines this horospheric subgroup. In particular, I think this gives you somehow a taste of the flavor of what happens. This is a nice theorem of Strombergson. So we have a point in SL2R modulo gamma, and we have some test function, and the integral from times 0 to t, the ergodic average of my function f along the flow, along this one parameter unipotent flow, is the average of f plus some error term. The error term, morally, you could think of it to begin with as t to the minus S1. S1 is determined by the lowest, smallest non-trivial eigenvalue of the Laplacian on the corresponding Riemann surface. But there is some, that's not quite true, in particular because there are orbits which are not equidistributed. So what you actually need to do, so you're basically averaging along some segment of a horocycle of large size. By definition for the horocycle, right, it's contracted if you apply the right direction of your diagonal element. So you start with a segment and you contract it to be of size 1. And you basically need to look at where your endpoint, so you start with the orbit of x, you apply an element of the diagonal group which contracts this unipotent segment to size 1. And if you are in a fixed compact region, then everything is fine and good. This is already Hedlund understood. But if you are far away, then your estimates suffer. And that's why this parameter r, which is some modified version of the length of integration, comes into this estimate. So this sort of gives you, I think, a good idea what kind of things can be said about unipotent, about horocycle orbits. There's another general class where there's a very beautiful, effective theory, and that's when you have a periodic orbit of a semi-simple group in the arithmetic context. It's important that you would have actually not just arithmetic, but congruence, because you want to use the Selberg type bounds on the uniform spectral gap. So here's some not completely harmless fine print, which, okay, we're going to ignore. But basically, you have a completely effective equidistribution theorem here, and it's slightly tricky to state because maybe you have a periodic orbit which is sort of very wide, let's say very big volume inside periodic orbit of a bigger group, which is somehow moderately wide inside the whole space. So you need to figure out whether you want to think of yourself as being very well equidistributed in this somewhat wild bigger orbit, or you're going to be equidistributed in the full space. And this is a way of phrasing it as this parameter v that you sort of change. And as you make this parameter lower and lower, the degree of accuracy you want becomes less good. But if v is lower and lower, somehow the excuses you're willing to find for why your orbit is not equidistributed become, you want better and better excuses. There's further work by Anzidler, Margulis, and Mohammadi, and Venkatesh, which allow the group H to vary. And somehow, whether you want it or not, if you want to allow H to vary, you need to think in the S-arithmetic context. And I guess if you want your group to vary, this is not step 0, this is step -1, just to somehow know what you're doing, but you need to some kind of notion of volume which would work, allow you to change your acting group. So obviously the volume of a periodic orbit would be related to the Haar measure of my group divided by the stabilizer of the point which you're periodic. But there's no the Haar measure, there's a Haar measure. The normalization of Haar measure is not canonically defined, at least not in this context where we don't have any Q structure on H. So what you want to do is to normalize the Haar measure somehow, and the best way to normalize it is by fixing some open, relatively compact neighborhood of the identity, and somehow you fix the Haar measure so that it would give a fixed measure to this compact set. And this is a good definition. Turns out that as your orbit becomes wilder and wilder, the volume becomes bigger and bigger. Okay, so these are two cases where we have a nice quantitative theory. So of course you want to go to a case where you don't have a nice quantitative theory, because that's what we do for a living. It's also important for many, this is a fundamental problem. The quantitative theory of unipotent flows is not just somehow a challenge for challenge sake, it's important for many purposes. Of course, the results that we have at the moment are relatively modest. Not relatively, are modest, but they are something. Another definition to be able to state what we want to do. So when you take, in Ratner's theorem, take an orbit closure, you get a periodic orbit of some group. You could actually say which group can occur. Not every group can occur. You would think your first guess might be that your group has to be generated by unipotence if you have some bigger group. And that's almost true, but it has to be actually generated by unipotence over the algebraic closure. Somehow, surprisingly, the algebraic closure comes into the picture. So a group is of class H, basically, if it's generated by unipotence over the complex numbers. And I'm going to, all of these effective results that I'm using are going to use the fact that integers are 1 apart, etc. So I'm looking at arithmetic quotients. So possibly one could imagine some of these things, or maybe all, I don't know, can be extended to the non-arithmetic context. I'm, in any case, simple-minded, and I'm interested only in, my motivation is mostly in looking at arithmetic applications, so arithmetic context is fine for me. These spaces, these quotient spaces that we look at, so I have a real algebraic group divided by some lattice, are not in general compact. As I define the situation, everything lives inside the space of lattices, SL and R, modulo SL and Z. So I can just have these compact subsets. These are the elements in G mod gamma. So the corresponding lattice does not have any short vectors. So for every delta, this is a compact set. And as delta becomes smaller and smaller, the compact set becomes larger and larger. And if you take the union over all delta, then you get the whole space. So this is some kind of compact, these are basically what you get. In other words, you have these k deltas are the spaces you get when you eliminate a delta neighborhood of the cusps in my manifold. And okay, I promised some kind of quantitative density theorem. You could see now that what I mean by quantitative. So the kind of quantification I would be able to get is of iterated log class. So a function is of iterated log class if it's at least a constant times log the parameter. Okay, so I can now discuss a bit the theorem. So this is an effective and quantitative, even if at a very modest quantification, density theorem for unipotent flows and in the arithmetic context. So I have a one parameter unipotent group. That's not a restriction. It's easy to reduce the general case to a one parameter case. So I have a one parameter unipotent group. Then there is some phi of iterated log class. So that now I have two parameters, R and T. R basically measures how good an excuse I require or how bad an excuse I'm allowing. And T basically measures how far in the orbit I'm going. And I have some point. Then at least one of the following two options hold. One of them is that I am 1 over phi of R dense in the space. I need to be a bit careful because the space itself is not compact, so I need to cut off but basically what we say that any point which is away from the cusp, I can find t, which is less than capital T, so that the flow at time t of my point x0 is a distance at worst 1 over phi r from the point, my target point y. So this is somehow the good situation. Then there's, of course, the excuses. So at first you might think that a good excuse, and certainly it's a good excuse, if your orbit throughout stays very close to some periodic trajectory. And that can happen, but that's actually not the most general thing that can happen, and you could see it already in the case of SL2R modulo gamma. What could certainly happen is that your orbit starts very close to periodic trajectory, and somehow as you vary the parameters, slowly the periodic trajectory evolves. So basically the best you could hope for, and that's actually what we have, is that if you chop your interval of time into chunks of size t over r, then each one of these chunks, on each one of these, you're close to periodic orbit of controlled complexity, height, volume, whatever you want. So that's the theorem. Number of logarithms, okay, that's somehow, unfortunately, it becomes worse as the dimension of the group is bigger. It's twice the rank plus the dimension of a maximal unipotent subgroup, -1 because you're given to begin with a one-parameter unipotent group, so you save this 1. Probably this 2 can be eliminated. It's not, I'm sure, anyway, this is what we currently are writing. If you apply this theorem for a fixed R, the quality of your excuse, let t go to infinity, and then let r go to infinity, it's not hard to deduce the full orbit closure rigidity theorem from this quantitative theorem. So it is indeed a quantitative theorem that implies a qualitative theorem. And I guess a key element of the proof is a robust notion of what it means for a point to be typical, some kind of Diophantine genericity condition, which is not an intrinsic property of the point, but it's somehow related to the point and the flow. And not just the flow, but also how far I want to go. So maybe I would comment a bit on Ratner's strategy in proving the orbit closure theorem and what we do, so that somehow I think that could be instructive. So what is Ratner's strategy? So you start with a point, any point, arbitrary point. And then you could look at these empirical measures. You take the empirical measure on a segment of an orbit of size capital T. That's typical routine one uses in trying to relate behavior of individual points to ergodic theory. And then you try to find a weak star limit point of these sequence of measures. And okay, if the space is not compact, that's already, there's something here to be said, because you don't want these orbits to diverge, to escape to infinity. That's actually the first rigidity result known for orbits of general unipotent group. That's a theorem of Margulis that this doesn't happen. So you would have weak star limit points, and they would be probability measures. So you're in a good shape. I mean, what you actually use is theorem of Dani, which is sort of development of theorem of Margulis. And now, okay, now there's a measure classification theorem. I'm not saying anything about how Ratner proved the measure classification theorem. That's okay. That's an involved story, and it's actually so. There are various routines you could do. You could sometimes get And one of the things which is completely unclear is why, if you apply all of these tricks that you could use, you eventually are able to classify invariant measures in general situations. So it's actually a case where proving the theorem in concrete special cases might, I mean, you'd need some further ideas to get to the general case. Anyway, so so you now apply a measure classification theorem. The measure classification theorem would tell you could only classify the ergodic measures. You could basically, the set of invariant measures is a convex set. You can understand the extreme points, and there are actually uncountably many, but they come in countably many families. So you could write your measure as countable sum of mui's, each one living on a immersed submanifold inside G mod gamma. And then you use the fact that your unipotent flow is polynomial in T to show that if somehow in the limit you gave positive measure to one of these submanifolds, then just because in the limit you gave positive measures to one of these submanifolds means that initially you were on this manifold and then you stayed there forever. And then you conclude that your orbit closure is homogeneous. The strategy that we employ, which is related to and motivated by the work of Dani Margulis from the late 80s, is somehow using this Diophantine genericity. I will explain what I mean in a minute, but it would be good, before I do that, to give some background to explain a result that I've already, the non-divergence result that I've already referred to implicitly earlier. So this is an important theorem, and it's in fact the first general theorem known on general unipotent groups. So they are both morally say that unipotent orbits cannot be divergent, but they say this in different ways. And the important thing here is to pay attention to the order of quantifiers. And I guess anyone who read a paper of Jeanne knows that part of the fun of reading a paper of Jeanne is to figure out in each lemma what is exactly the order of quantifiers. So here the order of quantifiers is important. So in this theorem, you start with a point in some compact subset of G mod gamma, and then you can find, somebody gives you a delta, you could find a bigger compact subset, so that if you start from this original compact set, you stay inside the bigger compact set most of the time. That's sort of the first statement. The second statement, you have a given fixed absolute universal compact subset of G mod gamma, so that every trajectory, maybe initially there will be some bad time, but eventually the good life would come into the picture. You would spend most of your time inside this fixed compact set that does not depend on anything, unless you had a very good excuse not to, unless you were maybe a periodic orbit of some unipotent, you were a periodic orbit of some unipotent group high in the cusp or something similar, unless you were on, this is a precise condition. The Dani Margulis, and there's also contributions of Shah, linearization method, gives similar results for avoiding periodic orbits. For periodic orbits that are not transverse to your flow. And the starting point of what we do is to define a notion of epsilon Diophantine up to time capital T. So in this type of linearization, when you do some kind of iteration, you start with some compact set, you somehow would have to, you can't really get back to the same compact set. You need to sacrifice something. But what we show using somehow ideas which are related to passing from to this statement in this Dani-Margulis theorem is that we define some notion of epsilon Diophantine up to time capital T with the property that as capital T becomes bigger and bigger, this is a more and more restrictive notion. But if you just care about an orbit up to time T, the actual real-life implication of having this Diophantine condition up to time T, or maybe upgrading to first class and having epsilon Diophantine for much larger time, do not make any difference. And this, what you get with this notion of epsilon Diophantine that we use, and so that's the basis of what we use, is if you have a point which is epsilon Diophantine, then in fact, if you, and our iterations, I mean, we somehow lose a lot, right? We get at the end rates which are log, 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 log. So what happens is that we go some amount of time with unipotent flow, we become happier by a bit, then we apply the argument again. This time we just go not up to time t, but up to time t to some power. So what this notion of Diophantine notion guarantees that if you're epsilon Diophantine up to time capital T, then if you look at your orbit up to capital T, most of the points in the orbits are going to be yeah, I somehow maybe have here, I should, if it's not epsilon 0 Diophantine, I should have here delta, not 1 minus delta. But anyway, most of the points in your, most of the points on your orbit up to time t are going to be epsilon not Diophantine, some absolute value, which does not depend on epsilon, up to some time, which is a power of t. And then, okay, I didn't want to get into too many details, but the basic strategy in a qualitative sense is the following. So I start with a unipotent group, maybe one parameter group, or maybe by induction I got a bigger group. I start with some unipotent group, and I have a subset of G mod gamma, which is invariant under this unipotent group and is closed. And I start with a point which is reasonable. So, okay, in the effective regime, I want to study orbits of size capital T, so my points x0 would be Diophantine up to time capital T or something. And you could actually define a non-finitary notion if you wanted that would satisfy what you want. And then for points inside my closed set Y that I'm trying to understand, I'm trying to show is basically has to be something simple. I am looking at which elements of the normalizer keep me inside my set. So there might be, obviously elements in my group are going to keep me inside my set, so let's just divide by them, and because I guess I'm looking at the normalizer, I can divide from the left or from the right at my pleasure. And then maybe there are other elements, maybe there aren't. That's somehow a set that I define for every point in my orbit closure. Good thing about this definition is that it's invariant under applying U, basically just by definition. And it is semi-continuous. So if I go, I never know it's upper semi-continuous, lower semi-continuous, but basically if I take I have points in the limits, this set can only jump up. I can have more points, but the points which I had earlier can't go away. And then, essentially, if you translate what we do to a qualitative language, what we do is to find a point inside the orbit closure of my original point, which is still Diophantine generic, which maximizes this quantity. So in the non-effective world, this set is going to be a compact no-ordained set, so it's not completely obvious why you could maximize some semi-continuous function on a set which is not compact, but somehow this can be done. And then once you maximize this function, then magical things happen. You suddenly have, so first of all, it's no, unless if you are epsilon naught, this thing certainly is not going to be just the identity. There would be more elements in the normalizer inside your orbit closure. And not only that, but in fact, you could get a bigger group. And if you are, what's really important is that unless you started with a horospheric group, you could in fact get a bigger unipotent group inside this set. And then, okay, then you apply induction. At the end of the day, you get to the horospheric case, which you understand even qualitatively without these horrible logs. Now, like I said, an early triumph of this theory was Margulis' proof of the Oppenheim conjecture. Let me tell you what the Oppenheim conjecture was. The theorem, Margulis' theorem is, so if I have an indefinite irrational ternary quadratic form, or I mean, in this business, the bigger, the more variables, the harder the easier the problem. So ternary is the hardest case. So I have a ternary quadratic form, which is indefinite, and I can look at the values this form gets on integer points. Let's say integer points which are non-zero, but less than capital N, and I take the absolute value of Q, and I want to see how small it can become. There's an absolute value, a hidden absolute value here. And the theorem of Margulis is that you could realize arbitrarily small values for this quadratic form. And it's easy to, I mean, there are certainly integral indefinite ternary quadratic form which do not represent zero non-trivial. So this condition on rationality is needed. And the relation to homogeneous dynamics, you basically present an arbitrary quadratic form up to a constant. You could present it as taking your favorite quadratic form composed with some linear map, maybe a map inside with determinant 1. And then if you care about the integer points, you basically care about not about this particular element, but about the SL3Z coset of this element, or the lattice it defines, its point in SL3R modulo SL3Z. And the point is rational if and only if the orbit under the symmetry group of this model quadratic form is periodic, and the form satisfies the Oppenheim conjecture if and only if the orbit is unbounded. Yeah, maybe I should note that with my definitions, periodic and unbounded are not mutually exclusive, but okay. So if you apply the general theorem about effective density of orbits, you would get some estimate to how fast or how fast this thing goes to zero, then goes to infinity. You would get from the general theorem something like log, 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 log n inverse. There's actually, you don't need the full orbit closure theorem. You could apply a trick of Dani-Margulis. And you could, we also give a more efficient argument, and we do better. So Margulis and I have a bound of the type essentially 1 over log to the power. Both of these results, there's always an orbit behaves nicely unless there's a good excuse. So to save time, I didn't write down exactly what a good excuse is, but basically it means that your form is very, very close to a projectively very, very close to a form with integer coefficients with small integers. And I guess a couple of months ago I got from Jean in handwriting a proof of a very nice theorem which is related. It's, not surprisingly, it's completely optimal. But it doesn't talk about every lattice. So what Jean proved is that if you have this, so you take this family of quadratic forms. Even for this family of quadratic forms, the only way we know to prove that every form of this type with alpha, at least one of alpha and beta irrational, attaining arbitrarily small values is through dynamics in some way or another. So even if you have x squared minus square root of 2, y squared minus square root of 3, z squared, this is not obvious how to get small points, and I don't think there's anything better known in general than what Margulis and I proved. But what Jean proved, that if you fix alpha and change only beta, so it's sort of an intermediate between taking a generic form and taking a specific form. So he allows himself onto this one parameter family of forms. You could get the optimal value of essentially this thing. If you take a ball of size n, you could find a point for which q, this point would be less than 1 over n, assuming the Lindelof hypothesis, which I think Jean hasn't yet proved, but unconditionally you have, okay, something which is maybe not optimal, but certainly orders of magnitude better than what we have for general form. Okay, thank you.